Thanks, Hamza. So in this talk, I'll give an overview of my current PhD project, which is in collaboration with Arlene Kim, Aditya Gunterboyne, and my supervisor, Richard Samworth. So to set the scene, I'll begin by giving an overview of the problem of density estimation, which unsurprisingly is a task of central importance in statistics. So the basic question we aim to address is the following. Given an unknown d-dimensional density f0, and a random sample x1 up to xn from that density, how should one estimate f0? Note that here we seek to estimate the entire density, not just the mean or some finite dimensional parameter. So one approach we could take is to look for a density estimate that belongs to a particular parametric family, such as the class of all d-dimensional Gaussian densities. But while the estimators that are produced in this way are often analytically tractable and or easy to compute, it's not hard to envisage situations where, say, a Gaussian assumption might be overly restrictive or inappropriate. On the other hand, fully non-parametric methods, such as kernel density estimation, do not assume a particular parametric form for the density estimate, which consequently belongs to an infinite dimensional class of functions. But one practical issue that arises is that these methods often require the choice of one or more tuning parameters, such as the bandwidth of a kernel. And for a practitioner, it can be troublesome to select suitable values for these, especially in multi-dimensional settings. So now we discuss an alternative, whereby one imposes a global constraint on the shape of our density estimate, not just a local smoothness assumption. And in what follows, we'll insist that our density estimate is a log-concave function, i.e. that its logarithm is concave. Now clearly this requirement makes sense in all dimensions, but if we specialize to the case d equals 1, it turns out that, roughly speaking, a function is log-concave if it is unimodal and has exponentially decaying tails. And in fact, the family of all log-concave densities is an infinite dimensional class that encompasses many of the most commonly encountered parametric families. So a slogan for log-concave density estimation is that it can offer the best of the parametric and non-parametric worlds. A significant amount of modelling flexibility is afforded to the practitioner, and at the same time it's possible to construct fully automatic procedures free of any tuning parameters for estimating a log-concave density. So one we'll focus on is the log-concave maximum likelihood estimator. So here we seek a density that maximizes the log likelihood over all densities f that are log-concave. And note that it's necessary for us to impose the shape constraint here, since without it we can make the log likelihood arbitrarily large by taking densities that concentrate probability mass in arbitrarily small regions around the data point, and therefore have arbitrarily tall spikes. It can be shown that the log-concave MLE exists and is unique with probability 1 whenever the true density f0 is log-concave and the number of samples exceeds d plus 1. And as well as being concave, log fn hat turns out to have a special, elegant geometric structure. It's an example of a so-called tent pole function, whose graph can be thought of as the roof of a taut tent stretched over some tent poles, which in this case happen to lie at the original data points. So in particular, the log-concave MLE fn hat is supported on the convex hull of the data, and it's piecewise log affine. And here are some plots. Firstly, when the truth is the univariate gamma 2,1 density, and secondly, when we sample points from a standard bivariate normal. Okay, so a natural question to ask at this point is, how good is fn hat as an estimator of the unknown truth f0? And to formulate this more concretely, we'll introduce a global loss function, namely squared Hellinger distance, which is defined as the squared L2 distance between root f and root g. Now, in their 2016 paper, Kim and Samworth studied the problem of estimating unknown log-concave density f0, and they showed that in the worst case, the expected squared Hellinger distance between fn hat and f0 is bounded above up to a constant depending on dimension by the following functions of the sample size. Note that these go to 0 more slowly than n to the minus 1, which is the rate that we'd expect in a finite dimensional parametric problem. And it can also be shown that fn hat has essentially the best possible worst case performance achievable by any estimator, and we say that it's almost minimax optimal in these dimensions. Having said that, we might expect that if log f0 is close to piecewise affine, and therefore has a similar structure to log fn hat, that the rate at which Fn hat converges to F naught in Hellinger distance is going to be much faster than the worst case bands on the previous slide would suggest. And very recently, it's been shown that this is indeed the case. So Kim, Gunter, Biener, and Sandworth showed that in the univariate case, if F naught is close to log affine, then we essentially get parametric convergence if k is small. And our ongoing work is addressing the problem of extending these results to multivariate settings, and we've been able to show that if F naught is close to log k affine and its support is close to a polyhedral set with at most n facets, then a similar result holds. And for more technical details, see our poster, and thanks for your attention.